Okay, so let's continue our lecture, and now we're going to the second part, which talks about complex function. So when we think about functions, for example, like real functions, we usually think about an input of real number and an output of real number. So in complex function, it's pretty much similar. It's just the input and output are both complex numbers. So think about z as a complex number. And then f is a function that takes complex number as input and a complex number as output. So I would say f of z also is a complex number. And that number obviously depends on z, otherwise probably don't usually call it a function. And we keep going, like this is a complex number. So naturally, we should be able to expand it into the real part and imaginary part. Right? So we can say this equals to some, like, this is the real part Kc and the imaginary part eta, and I'll just write Kc plus I it, where this Kc z is a real number, the eta of z is also a real number. So this is the real part of the complex function, and this is the imaginary part of the complex function. Okay. And we know that z actually equals to x plus iy, right? Where x and y are both real numbers. And in this way, z can be regarded as some sort of combination of x and y. So it is also fair to write the complex function in the way of like the real parts of x and y plus the imaginary part x and y. We can also write in this way and regard Kc and eta as a function of two variables. One is x, the other is y. And actually, in many cases, we have to write a complex function this way, especially when we talk about the properties of analytic complex function that we're going to discuss later. Okay, so in real analysis, there is a very important concept called the limit, right? So think about a real function. Let's say for real function fx, let's say if I say the limit of x approaching x 0, x naught of x fx equals to some value of, I'll give it whatever letter, for example like L, then we think about this definition. The definition follows the famous epsilon delta definition, which goes as, like, definition is for any epsilon greater than 0, I can use this symbol for sure. Here I'd say however small it is. This number could be very small, but it has to be positive. There always exists another positive number for which we call delta, such that for any x that is sufficiently close to the target of x naught, that is, when the difference between x and x naught is smaller than this delta, it always holds that the function value is sufficiently close to the target limit, and the difference is controlled by this epsilon. For example, this is the function and this is our limit L, like this. Right? And we'll say, however small your epsilon is, I can always find like sufficiently small interval around this x naught such that in here, as long as your x is like sufficiently close to x naught, then the value, function value, is always sufficiently close to the target limit. This is the definition of the limit for real functions. So in this limit, we have to be very careful that this x does not have to equal to x naught. It has to belong to this range, but it does not have to equal to x naught. I can define the function x naught, the value in here, and it still does not affect the limit. Right? Okay. So similarly, for complex functions, if we just look at definition, then it'll be exactly the same. Like for complex function of fz, if I say the limit of z approaching z naught of fz is some sort of L, of course this L has to be a real number, but this L could be a complex number, right? So definition, if for any epsilon greater than 0, there always exists some delta greater than 0 such that for any z, I would say for any 0 smaller than this absolute value smaller than delta, it always holds that the function value is sufficiently close to the target limit. It looks very, very, very similar, but we have to be very careful that, first of all, we are talking about complex values, right? If we are talking about real values, then for real function, this is the real axis, and there's some kind of function in here. And if this is your x naught, and when x approaches x naught, it either has to come from right or come from the left. Anyway, it has to be along the same line, has to be along the real axis. But for complex functions, remember the complex plane, right? Your z naught might be here, and your z can approach z naught in many, many, many different ways. It could go like this, or like this, or like even like this. There are infinitely many ways, and the limit has to hold for whatever way that your z approaches z naught. If I can find two different ways such that the limit is not the same, then this function has no limit at the point. Second, when I talk about this z minus z naught and fz minus L, remember that we're talking about complex functions. So z could be complex, z naught could be complex, the function value could be complex, and this L could be complex. So when we're talking about the absolute value, we're talking about the absolute value in the sense of complex numbers, right? So it is actually like the difference. If I talk about this is like A, this is B, when I talk about A minus B to the absolute value, we're actually talking about this distance, right? It is not just the real part or the imaginary part, it's a combination of them. So we have to be very careful. These are the two fundamental differences between the limit of complex function and the real function. Okay, so now think about some very common complex functions, like the basic elementary functions. For example, elementary functions. We could have exponential, for example, like e to the z, or maybe something to the z, something like this. We may have logarithm, like ln of z, for example. We might have power z to the 2, z to the 3, z to the n, or even z to the more arbitrary numbers. And we, of course, could have trig functions, sine z, cosine z, or even tangent z, or whatever. And we can have a lot of functions. But there is one thing that we have to be careful about. When we talk about real functions, when we have one input, we usually just have one output, right? For example, if we just regard all these z's to be real numbers, then output is unique. We know the meaning. However, when we get to complex numbers, things are not always so easy. Because remember that in the first part, we talked about the period of the argument, right? So, let's see. Z could be expressed as rho e to the I theta, or rho e to the I theta naught plus 2k pi, right? I just set this theta naught to be the principal argument, and this k could be any integer. These are equivalent. Okay. So, let's think about plugging these values into all these functions. And we'll instantly find that there are two types of functions that's going to give us problems. One is we call it the nth root of a given complex number. For example, like I would say z to the power of 1 over n. Let's just say we need to find some complex number whose nth power equals to the given z. Okay, so z is rho e to the I theta, or equals to this form. Let's think about it. If we take the nth root, or take the power to 1 over n, then z to 1 over n is, I take this form is rho times e to the I theta naught plus 2k pi, then to the power of 1 over n. Here, by default, rho is the absolute value, and rho is obviously real and non-negative. And I'll say, if I say rho to the power of 1 over n, this has very explicit, very certain meaning. But let's look at the argument part. If we look at the argument, that's e to the power of I theta naught plus 2k pi over n. Okay, this is where a problem occurs. K could be any integer. Let's see. If I just talk about z and I set this k to be integer, then theta naught plus 2k pi, 4k pi, 6k pi is the same thing. But when I have an n on the bottom, problem begins to occur. For example, I'll say like rho to the 1 over n as some kind of I'll just define wk equals to this value, whatever. Then w0 is rho to the 1 over n e to the power of I theta naught divided by n, no problem. w1 is going to be rho to the power of 1 over n times e to the power of I theta naught plus 2 pi over n. w2 is going to be 1 over n times e to the power of I theta naught plus 4 pi over n, and all the way to, I'll write it all the way to w of n minus 1. That is rho to the 1 over n times e to the I of theta naught plus 2 n minus 1 pi over n. Okay. If we look at all these values, we can easily figure out that all these numbers have exactly the same absolute value. The absolute value is just rho to the 1 over n. But for the argument, let's see. Theta naught over n and theta naught plus 2 pi over n. The difference between the argument is actually this 2 pi over n. When n is like 3, 4, 5, 6, 7, obviously, the difference between the argument is not 2 pi. So they are actually, this one and this one is not exactly the same number. Right? And for this one, the difference between this and this, another 2 pi over n in the argument. It's again not the same number, all the way until we reach wn minus 1. All the way here. If we continue, if we write wn, then it's rho to the power of 1 over n, then e to the I theta naught plus 2n pi over n. And we can find that this is rho 1 over 2 theta I theta naught plus n times e to the I, let's see, 2n over n, that's 2, so I times 2 pi. But e to the power of I times 2 pi is just the cosine 2 pi plus I sine 2 pi. So cosine 2 pi is 1, sine 2 pi is 0, so 1 plus I 0, that is just 1. So this goes back to 1, and we can eliminate this one, and this goes to what? This goes to w naught. With similar argument, we can figure out that wn plus 1 equals to w1, wn plus 2 equals to w2, and all the way. That is to say, if we calculate z to the power of 1 over n, we are going to get this many values. The value is not unique. So we have like n distinct values. Okay? From wn all the way up, we just get back to these values from the argument I just provided. So this function, z to the power of 1 over n, can return multiple values at the same time. That is to say, when we talk about complex functions, we need to be aware that there exists multi-valued function. This doesn't really occur that often in real analysis, but in complex analysis, we could see this all the time. Okay. So now let's do an exercise here. For example, if I want to find all the complex roots for this equation. Okay. So we can rearrange this equation into the form of z to the 3 equals to -8, right? And we're literally trying to find the 3 roots of like -8 to the power of 1/3. So according to the discussion here, of course, this is a multi-value function, and we're going to get equals to 3, so 3 distinct values. So to do this, the first step is, of course, to write this -8 as the standard form, like this, the polar form. So that's 8 times e to the I pi. We already know that e to the I pi is -1, right? Or maybe we can just use complex plane, this x and y. So -8 goes this way, so the length is 8, and the polar angle obviously 180 degrees, that's pi radians. Okay, so it's 8 times e to the I pi, and when I take the root, of course, I don't really write I pi, but I rather write pi plus 2k pi, and k could be any integer. Then I take the square root. Z is actually 8 to the power of 1/3 times e to the I pi plus 2k pi divided by 3. k could be any integer. But we have mentioned that there's a period here. The whole period of the angle, the argument, is 2 pi. So when I say 2k over 3, there is a period of 3 in terms of k. So I only need to care about when k equals to 0, 1, and 2. When k equals to 0, that is 8 1 over 3 times e to the I 3 over pi. That is 2 times e to the I pi over 3. So that's cosine pi over 3 plus I sine pi over 3. Cosine pi over 3, 1 over 2. Sine pi over 3 is square root of 3 over 2. So if plug it in and expand it, the result is 1 plus square root of 3 times I. When k equals to 1, it is just 8 over 1 over 3 times e to the I plug in k equals to 1, so that's 3 pi over 3, that's just pi. So e to the I pi. E to the I pi is negative 1, so this is obviously just negative 2. Finally, when k equals to 2, that's 8 to the power 1 over 3 times e to the I 5 pi over 3. And we do this. Cosine of 5 pi over 3 is 1 over 2. Sine of 5 pi over 3, negative square root of 3 over 2. So this is 2 times e to the I 5 pi over 3, and then just expand this. That's 1 minus square root of 3i. So in this way, we get all the roots. Okay. If you're talking about real numbers, negative 2 is the only root. But in complex numbers, there are 3 different roots. Okay, so you just have to be very careful. For this simple case of z to the power of 1 over n, where n is like 2, 3, 4, 5, 6, like the positive integer that is no smaller than 2, it's multi-valued, but at least the number of values is still finite. But there are cases in which the number of values could be infinite. Let's see. That case happens to be the logarithm. And for logarithm, when we talk about the ln of z. The reason we talk about ln of z is because in the polar form, this row is non-negative real number, and there is a factor of e here. So that can help us evaluate the ln of any complex number. So ln of z could be written as ln of rho times e to the I theta naught plus 2k pi. Right? And we use the law of logarithm. That is just the ln of rho plus the ln of e to the power of something. It's just this power. So it's plus I times theta naught plus 2k pi. And k could be any integer. And from this case, we can see that as the k goes through all the integers, there's no period at all. Now in the previous case, k has a period of n. That's when you add the value of n or 2 and 3n to the value of k, and it actually returns the same value. But in here, it's no longer the case. So there are actually infinite many values to ln of z. If you just take the principal argument, then the value is unique. But if you take all the arguments, there are really just infinite many. Okay? So for the case of ln z and the previously mentioned this case of z like 1 of n, these are the two types of multi-valued functions in terms of the basic elementary functions. Of course, if you construct more complicated functions, then there are tons of other multi-valued functions. So for multi-valued functions, there are two important concepts. One is called the branch point. The other is called branch cut. Okay, so let's look at this case. The branch point refers to some specific point on complex plane such that if the value of z goes around the circle around this point, then the function value does not return to the initial value. For example, in the case of z to the power of 1 over n, z equals to 0 is the branch point. Why? Because if you go around the circle like this, then you are actually increasing the argument by a factor of 2 pi. And when you take the root, so 2 pi divided by n will be the actual increase in the argument in terms of this value. And obviously, if you just increase the argument by 2 pi over n instead of like multipliers of 2 pi, the value is not going to return to the exact value. For example, if you take z to the 1 over 3, here you get a root, and then this argument goes to theta plus 2 pi, then the argument of z to the power 1, 3 is going to increase from theta over 3 to theta over 3 plus 2 pi over 3. An increase in the argument like this is not going to recover the same value. Right? Okay. Similarly, for ln of z, the branch point is again z equals to 0. Because if you go around the circle, then again, when you increase your argument, like when the theta goes to theta plus 2 pi, then your ln z is going to increase from ln rho plus I of theta, then it goes to ln rho plus I of theta plus 2 pi. And obviously, these two are not the same. So this is a branch point, and this is a branch point. Okay. So why don't we refer to other points as a branch point? Because, like, for both cases, if I consider any other point, so if we really look at any other point, and we go through a very small circle, then the argument can actually be confined in a very, very small range. So we don't really consider other points as a branch point. And of course, if you construct other functions, for example, like if you construct z plus 1 to the power of 1 over 5, then in this case, z equals to negative 1 is going to be the branch point. If you say like ln of 3z plus 5, and in this case, z equals to negative 5 over 3 is going to be the branch point. So that actually depends on your specific function. Okay. Now, the other concept is called branch count. For example, I still take z to the power of 1 over n as an example. Consider the positive half of the real axis. That corresponds to an argument of theta equals to 0. Of course, 2 pi, of course, 4 pi, 6 pi, whatever. Okay, and then consider a complex number z that evolves on a convex plane. Every time it passes through this cut, it kind of goes to a different range of theta. Like, for example, it started within 0 to 2 pi. But once you cross this cut, it goes to the argument between 2 pi and 4 pi. And if you go through it again, then the argument is between 4 pi and 6 pi. Right? So the multi-value of this function comes from the periodicity of the argument theta. And like when we go to 0 to 2 pi, that is like one part of the function. Then 2 pi to 4 pi, that's another part. 4 pi to 6 pi, that's another part. And when that goes around like this, like when I say z, if I write it explicitly, like z to the 1 over n equals to rho e to the I theta naught plus 2k pi. This is 1 over n, this is over n, right? So you literally have one value when your argument, this whole argument, is between 0 and 2 pi, that's when k equals to 0. And when this whole argument is between 2 pi and 4 pi, that corresponds to the case of k equals to 1. When this whole argument goes between 4 pi and 6 pi, that's the case of k equals to 2. So this cut is literally called a branch cut. And when we pass through the branch cut, we can consider the system to be like in another domain. Like the professional term is called Riemann manifold. But we don't really have to like care about the professional naming here. And for the case of log z, it's exactly the same because the problem still occurs with this argument, right? Okay. So the concept of branch point and branch cut. Okay. Now, from now on, most of our discussion will be restricted to one branch. And when we have multivariate function, we will be very careful to avoid the branch point or the branch cut as much as we can. Okay. So previously, we talked about the limit, and we addressed the issue of multivariate function that is kind of unique to complex analysis. Now let's think about it. In real analysis, we have the concept of limits, but we still have to go on, right? After we address the limit, we go into derivatives and integrals, right? And derivatives and integrals are basically what constructs the real value calculus. But now we're talking about complex function. So obviously, the similar concept still apply. We still have derivatives. We still have integrals. But the essence is going to be a little bit different. And we're actually going to talk about derivatives for this part, and for the integral, that is going to be for part 3 and even later parts. Okay, so we move on to derivatives. For real number, real functions, we think about f prime x, the derivative. So the definition is limit h goes to 0, f of x plus h minus fx divided by h, right? For complex function, formally the definition is still the same. I would write f prime at z is the limit of h goes to 0 of f at, z plus h minus f of z divided by h. But again, there is very fundamental difference. Because for the real function, this h has to be real, right? I've just mentioned before that this is x naught, and then just go through like this, right? So over here, the central point is x, and then h could be this way, h could be this way, and could be just approaching 0 along the real axis. But in this case, everything's complex. So h could also be complex. So h could approach 0 in infinitely many ways. The 0 is here and could go this way, could go this way, could go this way, or could be even much more complicated. This limit has to be the same regardless of the way that h approaches 0. If not, then the derivative of f is undefined at point z. Okay. For example, let's consider a very simple function of fz equals to just the real part of z, or we can say x, if z is x plus iy and xy are both real numbers. Let's consider this limit. I do the limit in two different ways. One, if h approaches 0 along the real axis, that is to say h is just a real number, then f of z plus h minus fz over h is just, this z is x plus iy, and plus h isn't a real number, so it is f of x plus h plus iy minus f of x plus iy divided by h. That is just, for this function we only take the real part, so that is x plus h minus x divided by h. And if we take the limit of h approaching 0, obviously this limit is 1. Now I consider another approach. I let h approach 0 along the imaginary axis. In this way, I define h equals to some I times big H, where this big H is a real number. In this case, I still take this limit, f of z plus h minus fz divided by h. That is, this h is I times big H. And up here, z is x plus iy, and this h is I times big H. So that's x plus I, y plus I, h minus f x. Remember that, sorry, fz. Remember that we are only taking the real part for this function. So this gives x. This also gives x. Down here is IH. And if we take the limit of h approaches 0, which translates to this big H approaches 0, this big H approaches 0, obviously this limit, the top part is already 0. So this limit is 0. That is to say, I have found two different ways such that when I evaluate this integral, it gives me two different values. That is to say, this function has no derivatives at all. If we talk about the real function fx equals to x, obviously this function has derivative and the derivative is just 1. But when we talk about complex function, that's no longer the case. So we have to be very careful that the requirement of a complex function to have derivatives is much more strict than for the real functions. Okay? So, after seeing this example, maybe we feel that, well, for a complex function to have derivatives, that's really not an easy thing, right? So, we need to dig into the condition for which the function has derivative. Let's see. To do this thing, we go back to the format of writing fz as real part cosine of xy plus I and imaginary part of xy. Okay. So in the previous example, I illustrated two different limits by letting h approach 0 along the real axis and the imaginary axis. Here, actually, we're going to do exactly the same thing. Let's see. First of all, I let h approach 0 along real axis. And if the derivative exists, that is the limit of h goes to 0. Because h approaches 0 along the real axis, h is just a real number. That translates to this, right? Because I think I'll just write the original form a little bit to avoid confusion. So f of z plus h minus f z divided by h. That is the limit of h goes to 0. This z plus h becomes x plus h plus iy. This is the new real part. This is the imaginary part. So f is cos A plus I eta. So cos A plus I eta. This part corresponds to f of z plus h. Right. Then I do a minus sign of f of x of z, sorry, I should write cos A xy, just the original xy. Over h. Let's rearrange the terms a little bit. That is just the limit of h approaches 0 of cos A x plus h y minus cos A of x y divided by h. Plus, here's a common factor of I throw it out. I times the limit of h approaching 0 of eta of x plus h y minus eta x y divided by h. I'm just rearranging the terms. But in this case, let's see. What is this? This term. Remember that x, y are real numbers, cos A and eta are real functions. So this is just the derivative in the real sense, right? So I just replace this with the derivative of cos A. Okay? So that is just the derivative of cos A. And y is the same, right? The change actually happens on h. Right? So since y is the same and we're changing the value of h, this limit actually translates to the partial derivative against x. Because when y is the same, we're just regarding y as a constant, right? So that is the partial derivative of x. Okay. For this part, well, technically speaking, I should probably write something like this to indicate that when we take the partial derivative of x, we are regarding y as a constant. But that will make the notations pretty messy. So I'm going to use a simplified notation just like this. And for this limit, obviously, the same idea, right? So plus I times partial eta over partial x. Okay. So similarly, if I let h approach 0 along the imaginary axis, it's the same principle, right? I evaluate this derivative again. That's the limit of, this time I'll just write h equals to I, like some delta y, okay, because it's the imaginary axis. And in that case, On the bottom, it is just when delta y goes to 0. On the bottom, I delta y. And on the top, because this time your h becomes I delta y, right? So I rewrite it as x plus I times y plus delta y. So literally the top becomes x stays the same, but y changes from y to y plus delta y, right? Plus I times eta of x and y plus delta y. This term obviously stays the same. And with the same idea, I can just put this I out here, right? 1 over I out here. And I can just perform exactly the same analysis as what I did here to conclude that this term is simply just partial cosine over partial y plus I times partial eta over partial y. And I can rearrange it a little bit. This 1 over I and this I cancels. So that is just the partial eta over partial y. As for this part, we know 1 over I squared is negative 1, right? So I squared is literally I times I. So I can just put this I to the right hand side, put it on the bottom, and we can see that 1 over I is just negative I. In this sense, 1 over I is negative I, so this is just the minus I times partial cosine partial y. Now, okay, this is just the result of letting h approach 0 from the real and imaginary axis. There's just the two approaches of the infinite many. But, look, I already have this requirement. One result is this, the other result is this. And for the derivative to exist, these two has to be the same. What can we conclude? And obviously, this real number plus I times real number minus I times real number. Obviously, we only have we must have these two equations. And these two equations are actually called the Cauchy-Riemann equations. Okay, so we only studied two different ways of h approach 0, but we already have these strong restrictions. Okay, but these are just two approaches, right? There are actually infinite many approaches, and we only studied two. So this condition, of course, it is necessary, but it is not really sufficient, right? So I'll add a little bit of new restrictions to make it sufficient. If you want it to be sufficient, you just need all these derivatives to be continuous. If all these derivatives are continuous, then this Cauchy-Riemann equations instantly becomes necessary and sufficient conditions for derivatives to exist. For the purpose of this course, I'm not really going to dig into the details of this proof here, because we don't really need that for the later discussions. We just need to remember them and just need to use these conditions. Okay. Now, moving on. So these are the conditions for derivatives to exist, and only some complex functions have derivatives, right? But actually, the functions with derivatives are not really only a very small number of the complex functions. all the functions I have listed in here, all the basic elementary functions actually have derivatives. For example, if you talk about e to the z, then the derivative is just e to the z. If you talk about ln of z, take the derivative is just 1 over z. If you talk about sine of z, take the derivative, it is actually just cosine of z. If you talk about cosine of z, take the derivative, that is just negative of sine of z. It all looks pretty much similar as in real analysis. And we can just use the same rules in here. But always remember that it's complex functions, so the essence is still a little bit different. First, the definition of some of the functions here might be a little bit tricky. For example, for sine z, how should we understand that for complex values? We should use trig identities. So it's not a trig identity, but it's Euler's identity. So e to the iz is cosine z plus I sine z. This is true even for complex z. Z doesn't have to be real. And e to the negative iz is cosine z minus I sine z. So basically, sine z is e to the iz minus e to the negative iz divided by 2i. Okay, if z is x plus iy, then you have to expand it into e to the I x plus iy minus e negative I of x plus iy, 2i. That translates to e to the ix minus y minus e to the negative ix plus y divided by 2i. And here, x and y are both real numbers. So this is what? This is just e to the negative y and e to the ix. This is just e to the positive y times e to the negative ix. And for this part and this part, you just further expand with e to the positive or negative ix equals to cosine x plus I sine x. And this is the exact meaning of sine z. For cosine z, you just repeat the same analysis, but replace this 2i with 2 and replace this minus sign with the plus sign. And we just do similar things, right? So first of all, the definition is a bit tricky, and we should no longer use our understanding of real functions to understand these complex functions. And also with the analysis, we can see that sine z if z is real, this is true. But for complex z, this is no longer true. Similarly, cosine z, no longer true. It could go to infinity. Okay. And also, I write ln z prime in here, right? But remember that ln z is a multi-valued function, right? So we're still taking a derivative, it doesn't really matter. The point is we have to restrict our analysis within one of the branches. We can't go cross branch cut when we take the derivatives. So for example, if we fix the argument to be within 0 to 2 pi or within 2 pi to 4 pi or 4 pi to 6 pi, we're all good. But if we cross the line, we have to be very careful. Okay, so all these basic elementary functions actually have derivatives. And in this case, we are going to proceed to the next part where we define something like analytic complex function. So the definition of analytic complex function looks very straightforward. Think about a region in the complex plane. So if the derivative of the function exists for every point in this region, then we say that this function is analytic in this region. Okay. So an analytic function is a very useful type of function in all complex functions. And of course, the region D sometimes that depend on the function itself. For example, if you talk about very good function e to z, cosine of z, sine of z, or even like I'll just write some polynomials of z, whatever. All these functions are actually analytic throughout the whole complex plane. Yeah, but if we talk about, for example, z plus 1 over 1, then obviously problem occurs at z equals to -1, right? So for this function, it is analytic in almost all places except this point. For another example, let's say x z squared plus 1 over 1. If z is a real number, it's all good. But it's complex, right? So z squared plus 1 could be 0, and the roots are obviously z equals to plus and minus I. So this function is analytic in almost all places except I and negative I. So if I say, for example, for this function, it's analytic in here, it's good. But if the region looks like this, it's not good. For this function, if the region looks like this, it's not good. But if it looks like this or looks like this, it's not good. Okay? And sometimes we can talk about like a more endless-like region, for example, in here. Maybe some function could be analytic in a region like this, or even in a region like this. It's all possible. We don't have to just talk about like one single chunk of region. You can just have like inner blotches in it. It's all good. Okay, so let's think about analytic function. We know that for analytic function, if I write this f in terms of cosine of xy plus I eta of xy as always real, and then the Cauchy-Riemann equation gives it's this partial cosine over partial x equals to partial eta over partial y, while partial eta over partial x equals to negative of partial cosine over partial y. Cauchy-Riemann equation. This has to be true. So when this has to be true, let's conclude a few properties. First of all, let's calculate it should be this derivative to the squared and partial eta over partial x to the squared. Let's see. This partial cosine over partial x to the squared can be replaced by this partial eta over partial y squared. Right? On the other hand, we could also say if I evaluate this, then I can replace this partial cosec or partial y to be. So let's try to evaluate these quantities for complex and analytic complex functions. So first of all, we have derived the CR equations based on this identity, right? So we think about the definition of absolute value of a complex number. So if the real part and the imaginary part, we take their squares, we add the squares up, and we take the square root, that is the absolute value, right? So in here, obviously, if I write this, then from this identity, we can see that both quantities should equal to the absolute value of this derivative to the power of 2. Is the absolute value squared. Thus, it's real part squared plus imaginary part squared. Here is a negative sign, but in the square, the negative sign doesn't really matter. Okay. Number 2, let's evaluate these two derivatives. So for this one, partial squared cosec over partial x squared, we rewrite it in terms of partial over partial x of should be partial cosec over partial x, right? Because we are taking second derivative of x. But now we use the CR equations to rewrite this. I don't write partial cosec over partial x anymore, but I write partial eta over partial y. For the second term, it's partial of partial y of partial cosec of partial y, but again, I use the CR equations to rewrite this partial cosec over partial y as the negative of partial eta over partial x, and here's a negative sign. Because there's a negative sign, I change this plus sign to minus sign. So we compare these two terms. We find that this is take the derivative of y and then x. This is take the derivatives of x and then y. But for analytic complex function, all function has to be continuous, has to be smooth. So when take the derivatives, the order doesn't really matter. Partial y, partial x, partial y. It's the same thing. This becomes 0. And the same principle, this derivative becomes partial over partial x of partial eta over partial x. I write it as negative of partial cosec over partial y. And over here, partial over partial y, it should be partial eta over partial y, but I write it as partial cosec over partial x. And the same thing, the same function, we're just interchanging the order of the derivative, which doesn't matter, so this should also be 0. So that means cosec and eta, if we regard it as functions of x and y, then they both have to be harmonic functions in the complex plane. Because this is 0, this is 0. This is literally the definition of harmonic function. And finally, let's evaluate the dot product between the gradient of cosec and eta. We can easily write out the gradients and then take the dot product as this. Okay. And over here, so this partial cosec over partial x is equal to partial eta over partial y. And this term, I leave it as it is. Plus, this partial cosec over partial y is negative of partial eta over partial x. Is negative of partial eta over partial x, then partial eta partial y. And obviously these two terms should cancel and we should get a 0. That means the gradient of cosec and eta should be perpendicular to each other because the dot product is 0. That is to say, if I draw the contour of cosec and I draw the contour of eta, then the contour should be perpendicular to each other everywhere. Okay. we can see that complex functions do have very special properties that like general functions don't really have. And we also know that many basic elementary functions are analytic. So these properties are going to be very, very useful when we further discuss the integral of complex functions. So this is the end of part 2.